Before we get started, I'd like to spend a few seconds on myself. I'm Niklas Haas. I work as an independent consultant in the multimedia sphere. If you recognize my name, it's probably from projects like Libswscale VDD or FFmpeg. And I want to talk to you today about my SDF 2024 project, which was all about improving SWscale, which, if you don't know, that's a central component of FFmpeg that's used for converting pixel formats and scaling. So, I don't know how much you know about SWscale, but I want to just briefly sort of build the motivation on why this project even existed and what problems I was trying to solve. And because I know some geomasochists out there like some techcore, so. Well, SWscale, it's an interesting library. It has an API that I could generously describe as colorful. You know, you have to sort of set up all of your parameters about the exact transformation you want to do by hand, which of course, I mean, nobody's going to do that correctly, right? And of course, you know, that's just the easy parts, because then you have these weird sort of get and set functions that the API would imply you could be able to call at any time, but actually, if you call it at any point other than exactly in between init and scaling the first run, it completely breaks. So that's always nice. The internal design also isn't exactly my favorites. You know, you have the classic FFmpeg anti-patterns of having a gigantic context struct with several hundreds of state parameters that then recursively contains itself as subcontexts and cascaded contexts, and you know, each of those cascaded contexts is recursively calling into its own internal functions, which then calls back into the main context, which then calls into some scale gamma function, which then, depending on what other condition flags are set, basically the whole thing was a gigantic mess, and it took me quite a while even just to understand what the actual code flow is inside SWscale. So yeah, that's one of the problems I tried to solve. The other problem I really had with the library was that all of the pixel format conversions were done by like a million special paths. So instead of, you know, FFmpeg has several hundred pixel formats, and of course, what SWscale decided to do was we should just have an init function that's several thousand times long, which just goes through, if source format equals X and destination format equals Y, then use this very specific function to convert. And of course, these functions, each of them recursively contain others, dozens of sub-functions, which have all these specialized paths. You know, every path has its own bit or matrix for some reason, then you have the randomly putting in the NDNS concerns where it somehow means that the function should be for a different channel order in this specific case. And so basically, it was at a point where I think a lot of people would agree that the library was almost impossible to extend. It had a lot of random bugs, you know. You had highly unpredictable behavior because the performance was all over the place depending on whether you hit this specific fast path or not. You know, even from an API user point of view, it made no sense that if you have two formats which are almost exactly identical except for one small difference, like maybe the channel order is swapped, you could be hitting a completely different path internally and getting completely different performance, right? Some paths were writing past buffer line ends, others were not. You know, some were rounding correctly, others were differing, and the whole thing was a gigantic pile of bespoke, unpredictable functions. So that's sort of the state I was in. What was on my plate at the beginning of the project. So let's talk a bit about what I tried to do to fix it. So first of all, I wanted to sort of start with a external experience and then work my way down the layer of onion. So one of the first things I did was I created a new public API where the design was, instead of having all of these complicated init procedures where you need to set all of your scaling parameters by hand and set the correct chroma offset values for interlaced frames by hand and so on. The new API works like this. You just have a single context object, which is now public, and it has basically just settings that affect how the transformation should be done. And then you have a single main entry point just called Swscale frame. And the way you use it, this is code from the new VFscale as of current Git master. You just set your frame properties, which you know you have to do anyways, and then you call Swscale frame, and everything else is handled automatically. So it's also one of the ideas is that you shouldn't need to initialize the context if one parameter of the frame changes. The context should be able to reinitialize itself automatically if the format changes in a way that requires reinitialization. So with that out of the way, I decided to sort of work my way down the abstraction hierarchy. Starting with the external API that is just dealing with, okay, you're ingesting frames, figuring out what are the frame properties and so on, what do I even want, what does the user even want me to do? And then I wanted to create a clear sort of levels of abstraction internally. So on the level below the frames, you should figure out, for example, is this frame interlaced, and if so, split it into two subfields. What are the requirements for this field? Like, for example, the AV frame has a classic problem where a lot of parameters are sort of ambiguous, and sometimes they're relevant, sometimes they aren't. So that's sort of the layer where I decide what actually relevant properties are there. Can we fix them? Can we normalize them? Can we add things like metadata from side data and so on? Then on the level below that, we want to be asking questions like, okay, so I know from what format to what format I want to convert, so how many conversion steps do I need, like sort of on a high level? And then finally, once you know how many conversion steps you want to be performing, then we should do the actual pixel conversions. So instead of having this one gigantic init function with thousands of conditions and logic interwoven randomly, my goal was to create a clear hierarchy of abstraction. So one of the abstractions I ended up coming up with internally is something called SWS graph, which is sort of the design you'd obviously come up with if you were designing it from scratch. So if you have multiple scaling passes, instead of these cascaded embedded contexts that recursively call into other contexts, you just have a clear separation between different passes. So for example, currently we might have a pass that converts to RGB, then a color management pass if you need to convert between primaries. Then you might have an XYZ conversion pass, and finally you might have like final output gamma lookup table pass, which is one of the things that these cascaded contexts were needed for in the first place. So I ended up implementing that, and that also took care of a lot of other weird problems. Like for example, now you have the ability to mix threaded passes with non-threaded passes, because each pass sort of can control how it wants to be threaded independently. And generally that sort of gave me that got me to the point where each pass was self-contained, and the state from one pass wasn't affecting state from the other pass and so on. So that gave me a pretty good point where I was comfortable then to start working on actually improving the low-level format conversion logic itself. So that's what I want to actually spend the bulk of my time on, is the new pixel format conversion code that I developed. So to give you a bit of I guess to recap the problem a bit, so FFmpeg has a lot of pixel formats, and if you have hundreds of pixel formats and you want to be able to convert from any pixel format to any other pixel formats, obviously you have like over 10,000 possible combinations. So it's obvious that the old approach of just having one specific conversion function that is handwritten in assembly for every single possible combination doesn't scale at all. Another thing you might think to do, okay, what if instead of having a dedicated fast path for every possible combination, what if we had just one fast path to decode a format and then one to encode a format and then choose some common sort of intermediate format? That's actually something FWscale also currently still does when you're scaling. It always goes through like 19-bit YUV or something. It's a bit awkward, but I mean that works. It's better than the previous, but it's also not really nice either. Like you still have the problem of you have a lot of picture formats which are just very similar to each other, and then you need to start like templating the hell out of it or whatever. Like, and there's also no like what would you pick as the intermediate? Currently, FWscale goes through IUV, but that's obviously bad if you're converting from RGB to RGB. You eat the conversion for no reason. So what I wanted to do is I wanted to sort of end up in a state where what if instead of having a dedicated fast path for every pixel format, what if we just had some sort of common palette of operations that we could then combine in the order that's needed for any given conversion operation, right? So ideally, I wanted also to try and keep the number of operations that we actually need to implement in assembly like as low as reasonably possible. So I tinkered with the design a lot, and I ended up coming with something that I called SWSOP, and just to sort of give you a bit of flavor on like what these operations actually end up looking like, and I'm going to go quickly through the list. There's not a lot of them, I promise. So you have your classics like reading and writing pixels from memory. You have your byte swapping for big endian, little endian conversions. You have this weird sort of pack-unpack operation, which is just for taking like non-byte aligned data and sort of moving that to be byte aligned. You have sort of general pixel manipulation operations like clearing a pixel to a value, left shift, right shift, swizzle operations, which just change the channel order. Some of you might be thinking that's maybe a bit of an odd operation to include here, but with the way we ended up implementing it, that's actually basically a no-op because we're just swapping pointers around. You have a converts operation, which is for converting between pixel formats, obviously. You need something like that. For example, if you need to go from 16-bit integer to floating point or back. There's also a special case if you're going from like 8-bit to 16-bit, you sometimes want to duplicate the byte instead of just shifting it. Finally, you have a dither operation, which is just adding like a constant matrix to the pixel values. And for the actual conversion logic itself, it turns out all you really need is a sort of generalized linear transformation operation, which is internally represented as a 5x5 matrix. You have your scalar multiplication, which is just a fast path for the previous special case. That's just sort of needed for to make the internal optimization a bit easier. And finally, you have your minimum and maximum operations for clamping pixel values. So it turns out those 12 primitive operation types are all that I needed to implement any pixel format in Libswscale. So the question is, okay, we have our palette of primitive formats. Now, how do we actually use them, right? Like you still have the problem of, okay, I have 10,000 possible combinations of formats. How do I generate the right series of instructions for every format? And sort of the design goal I had is I wanted there to be ideally only a single code path, right? Instead of this thousands of if branches and conditions, I wanted there to be a single, like short, high-level, understandable code path that you can reason about and find bugs in like easily. So then I had a bit of a stupid idea, or maybe not stupid, depending. What if we defined all format conversions in sort of the most naive way possible? So you just take your inputs, you apply like a fixed series of steps to go from whatever input format to some like very friendly, generalized, abstract internal space. So like think normalized floating point RGBA from 0 to 1 range, linear light, like everything that you would want to have as an intermediate format. And then you do the same step, a series of operations in reverse to go from the intermediate format back to the output. So I mean that would basically guarantee that you get a correct conversion in whatever case, right? Obviously it's not very efficient if you're thinking about going through floating point RGBA for every possible pixel conversion. So what if then we applied a second step where we took this series of operations, this sort of very generalized operations, applied a little magic wand optimization to it, and that, hey presto, gave you the efficient direct implementation that you want. And so I tried that approach, and well, because I'm talking to you about it, you can probably infer that it ended up working quite well. I'm just going to give you an example of what that looks like in practice. So say you're taking 8-bit grayscale and you want to output RGB48, something does every day. The general code sort of does always its stupid step of instructions. So you read your one 8-bit value. You then clear all the remaining channels to 0. Then you convert that to floating point. Then you apply a 5x5 matrix to make it RGBA. Then you apply another 5x5 matrix to make it RGB16. Then you clamp it to the final output value range, convert it from floating point back to 16 bits. There would normally also be a dither operation somewhere there, but like just the way it's written, by default we don't dither for 16-bit output, but that's just a technical detail. And you take your 16-bit values, write them back to memory, right? Like that works, and you can probably follow along what's going on there. And then we apply a series of, almost like a compiler, we apply a series of, I guess compilers would call that peephole optimizations, where we look at, for example, we have two instructions following each other that have a very specific interaction, and like you can simplify that. For example, if you have two linear operations in a row, you can just multiply the matrices together. If you have, a clear followed by another operation, you can swap them to make the clear go later and propagate constants, right? So I'm applying a lot of these sort of primitive optimization steps that each one independently you can reason about and sort of prove to yourself that it's correct, basically. And in the end, if you do that enough times, hey presto, you end up with this optimized sequence, which is just an 8-bit read, then an expand operation to take those 8 bits and full range shift them up to 16. You swizzle it onto all 3 channels, which is like just duplicating the value 3 times basically, and you write that as 3 packed integers in memory, right? Like that's, in terms of the logic that's going on, that's basically the optimal instruction sequence. So I was really happy with that approach because you end up getting a lot for free, because all of the complicated logic isn't in the pixel format handling, but it's in the optimizer. And the optimizer is, you get all pixel formats for free, right? Like if you have a good enough optimizer, you can get any pixel format conversion optimized into whatever efficient sequence exists for that pixel conversion. The next logical question to ask, of course, is, okay, we have our series of operations that came out of this optimizer. Now how do we actually apply them to pixel values in a way that's efficient, and more specifically in a way that can actually compete with handwritten assembly? Like that's the goal, right? You want to beat Libswscale, not just, So, I mean, the first thing you might think is, okay, obviously I'll just define a function for each operation and just apply them in sequence, right? Well, I mean, sure that works, like in the proof of concept, but some of you might already be thinking like, okay, obviously if you're reading the full input image, just to apply a left shift by 2 and then writing the full result back to the memory, obviously you're wasting most of your time on doing just input and output operations and not actually gaining anything. And that sort of also conflicted with the idea of, hey, I want these primitive operations to be as, like, ideally I want them to map onto single SIMD instructions, right? Like I want to be able to build my optimal SIMD pipeline on the fly. So I want really, really small operations, but at the same time, you have many operations, but at the same time, you can't take the types of writing to the buffer every single time. The next thing I thought to try was, what if instead of writing the entire buffer, each operation only operated on a small chunk of data at a time? So you might say, let me take my image and sort of loop over the image in small chunks, like for example 32 pixels at a time, something that can fit comfortably in L1 cache. And we then just iteratively call every operation on just that pixel chunk, and then write the final output back to the destination buffer, right? So I implemented that. It works. Like that's already good enough to beat all of the C code in Libswscale, right? Like that would be a workable design. Although it was still a bit slower than handwritten, tight assembly loops. So I was like, well, I'm not really satisfied with that. And it turns out one of the big problems with this design actually is that if you have a sort of main dispatch function that has to, for every 32 pixel chunk, call like a dozen operations, right? Do the math for a 4K frame, that's a million function calls per frame. Like, I mean, some C++ programmers might think that's not too bad, but you have to realize these are like indirect dispatch, because you have a loop that's loading a different address every time and then calling that address indirectly, and that's the worst pace possible for a CPU prediction. So you eat up a lot of time actually just on the call and return overhead. So that's when I had the idea for my final design, which is what if each operation, instead of returning back to the caller, and sort of writing its data back to L1, what if each operation could just directly give its data to the next operation and just immediately go there, right? Like ideally you want to design like this, where you have an operation that receives some inputs and then computes some result from that and gives that result directly to the next operation, and that operation gives it directly to the next operation, and that operation writes it to the output buffer and then returns to the caller, right? So if you're familiar at all with functional programming, you might recognize that as sort of continuation passing style. So instead of returning back to the caller your data or writing it to memory, you take the data and call the next operation with the data that you computed. So that's what I ended up implementing. That's what is in Libswscale today. If we look at what that looks like in C, for example, this is a sort of highly simplified example of the code that's currently in Libswscale. You have an operation. Let's look at a left shift again as an example. It receives its pixel data from the previous operation, and then it also receives like the continuation that it should call when it's computed its result. So what it's doing is, it's loading its shift amount from constant data. It's applying that shift amount to the pixel values, and then it's directly jumping into the next operation. One of the big advantages of this design is that actually, because each operation sort of directly calls the next operation, you don't even have to have a single API for each operation. So each operation could have a different signature also, because when you're building your operation chain, you know what is the next operation. You can directly have the correct signature there already. So that frees you up to do things like, for example, custom calling conventions, which, if we go one step further, is what we do in the x86 backends. So instead of writing back to L1 cache or memory, we want to ideally keep our data in the vector registers directly, right? So we use a custom calling convention internally, where we just have a fixed set of vector registers where we input and output our pixel data, always in that order. And so if we look at the same left shift operation, now in assembly it's just, okay, it's loading the shift amount, you kind of have to do that anyways. It's applying that shift amount to the pixel values, which is the operation that you want to do, right? And then the only thing that's extra is the sort of 3 instruction epilogue, where what you're doing is you're loading the next address of the next operation, you're bumping the pointer by 1, and then you're jumping to that address, right? So that actually turns out has like almost no overhead whatsoever, because the only thing you're doing is you're loading like a linearly increasing set of addresses, which the CPU is very happy to do. You're doing an add, which is basically free because all of your like the bottleneck is in the vector ALU, right? And you're doing a fully predicted jump because every single operation has its own jump instruction. That means the jump predictor is very happy to just memorize the exact sequence of operations that are being called. So you also get rid of that indirective cache overhead. So in the end, all of the overhead is basically free. It's like fully predicted with wasting no time whatsoever on unnecessary read and write instructions. And as a consequence of the fact that now we only have to worry about these 12 primitive operations, we also are free to spend a lot more time, optimizing them from every possible combination of SIMD feature sets. Like in practice, I even do things like grouping together multiple registers. If you have, if the byte size is small enough that you can fit more and unroll multiple chunks at the same time. There's a lot of things you can do just because we are free to focus on only these 12 primitive operations and don't need to worry about anything else. In fact, the only sort of downsides I see in the current design is that sometimes you have a bit of redundant setup work where you may be missing a cycle or two that in theory could be avoided if you could move the setup further ahead. And also, as a consequence of the fact that I use the sort of internal calling convention where you have pixel data and fixed registers, if you're dealing with very packed pixel data, like RGB, you end up having to do a bit of unnecessary lane swapping and lane shuffling, which is just sort of a consequence of how ADX is designed. It's not really happy to directly loads packed data like that. Although the last point is something you can also improve. I have something called a packed shuffle solver, which I don't really have time to get into it fully, but basically the idea is because we have this sort of list of operations, we can do a lot of analysis on this operation list to find fast paths that exist for this specific conversion also. For example, in this case, if you look at what's happening on the data level, you're basically just taking an 8-bit value and sort of splitting that 6 times in a row, because technically that's what converting gray 8 to RGB 48 looks like. And in this sort of specific cases where you're just moving data around within like a chunk of pixels, you can do that very efficiently with CPU shuffle operations like pshuffp on x86 and so on. And so I have also something that's called a packed shuffle solver, where you just you generate a mask of your input byte positions. You can sort of apply these operations ahead of time, to this mask directly. Like this is all done during init time, basically. And then at the end, you can see, oh, actually, it turns out in this case, I can just take that result a little bit as a pshuffp mask and sort of dispatch that as a tight loop. If any of that flew over your head, don't worry about it. But basically, it means that we can beat all of these sort of handcrafted SIMD loops in a gigantic variety of special cases that are being discovered automatically because we have this operation list that we can then optimize into and feed into this analyzer. Like it's all being done automatically without any sort of check for any specific pixel format, right? So it just works for whatever pixel format. If an efficient conversion exists, the optimizer will find it, and if the optimizer finds it, the packed shuffle solver will implement it efficiently, right? So that was like the last puzzle piece I needed to actually beat Libswscale in all code paths, spoilers. So benchmarks, how does it actually perform in practice? Well, the overall speed up compared to across every single pixel format that exists is about 3 to 4 times faster. Although that's a bit of a that average is being pulled down by a lot of pixel formats that are less interesting. For more interesting pixel formats like classic converting YUV to RGB24, it tends to be something like 5 times faster. That's 5 times faster than the SIMD code that Libswscale was using before. If you are replacing a C implementation, it's usually more like 10 times faster or 20 times faster. There's actually some funny cases, there's this one case where if you're converting this specific BGR4, which is like a 1 bit packed into a byte to a different channel order, it turns out it's 758 times faster. By the way, for Onyx, that's not 758%, that's 758 times faster. Just as a consequence of the fact that Libswscale didn't consider this conversion at all, and so it just goes through the fully general path where it decides, oh, actually it's a 4-bit output, so we need ordered dithering, and the optimizer sees that dithering is unnecessary here because you're not gaining, you're not losing information, so why should you dither, and just eliminates that operation, and so you end up with 758 times faster code. If you're wondering, is it ever slower? Well, yes, there are some cases where the new code is actually slower than the old codes, although in my defense, in almost all of those cases, it's because the new code is actually doing something more correct. Like, for example, in this case, the old code was like, well, you're going from 5-bit to 6-bit. Clearly, I don't need to dither it, right? You're not losing bits, but if you look at the math that's going on, actually you are multiplying by a fractional constant. So you do end up with fractional pixel values, which the old code will happily just shift away and you lose data, right? I mean, sure, it round trips, but the result doesn't look correct. So the new code, in this case, the optimizer sees actually I can't eliminate this dither, so actually I do have to dither. So actually it is slower, but it's slower and more correct, so pick your poison. And if you don't like that, just disable dithering. Nobody will care. So I guess more benchmarks, if you're looking at how is the x86 backend compared to the C implementation, I have 2 backends currently, the C template backend, which works on all platforms, and then the x86 backend. On average, it's 5 to 6 times faster than the C code, which, by the way, is lower than it could be because the C code is written in a way that the compiler is actually pretty good at auto-vectorizing it, because you're sort of just doing a left shift on 32 pixel values. Like that's the ideal case for the compiler to recognize that, hey, actually, you just do a SIMD instruction here. So all you're really gaining is sort of not having to do I/O operations. So yeah, the x86 backend I'm quite happy with. So where does that leave us? Where do we go from here? Well, one of the things we can do, and that's actually something that Ramiro Pola is working on, or was working on, is you can take this series of operations and you can just directly generate assembly on the fly, like basically what browsers or emulators do, right? Because I mean, basically what we're doing is we're creating a bytecode language and then emulating it, much in the way that a CPU emulator actually would do it. So if you just convert that on the fly, using it for something like Asmjit, you can directly create a type loop and eliminate even that jump and load and add overhead. So that's an interesting thing you can do. You can of course also just directly convert those operations to SPIR-V, for example, and run it on the GPU. That's something I'm personally excited to see happen. Finally, you may have noticed I didn't really talk about scaling much, just format conversions, which is kind of a bit embarrassing because the library is literally called Libswscale, but currently it doesn't handle scaling. There's a lot of like subsampling, which I include as part of scaling, like lookup tables for something like PAL8s or other sort of edge cases that I just didn't get around to as part of the project because the scope was limited. So that's something that, I mean, none of that is insurmountable, just it has to be done. So if you do want to help see this project grow, first of all, more SIMD is always needed, especially if there's no current backend for Neon or RISC-V. If you do want to contribute, feel free to reach out. If you want to test it, I'd be very interested to hear, user experiences. Like, is it actually faster for you in practice? Do you hit any bugs? It's currently gated behind the unstable flag, so you have to actually enable it to opt into the new code. And lastly, if you're a company and you do want Swscale to be 3 to 10 times faster, please reach out, and this is your time to shine and help sponsor some open source development. So yeah, that's all I have prepared for today. Thank you so much for listening, and enjoy the rest of VDD. And if you have any questions, feel free to ask them either now or reach out to me in the break or later.
One question.
Yes.
For the SIMD, just now you're talking about using the JIT, right? I read through all the Neon stuff. It's really difficult to do RISC-V. And I think the RISC-V even more complicated. And you have a variable length, different chipset have different length, right? Mm-hmm. That's complete chaos. I have no idea how you're going to fix one library and can deal with all different fragmentations.
Right. So the question is, I guess, how would you design a RISC-V backend?
Or generally SIMD backend.
Given the fact that RISC-V implementations wildly diverge on the actual vector length.
Yeah, exactly.
Well, I sort of planned for that ahead of time, actually. I think even RISC-V would be easier to implement than x86 because the architecture is pretty loose in terms of what vector length it wants to run on, because you have this, at the fundamental level, what you're still doing is you're iterating over 32 pixel chunks, right? In reality, that's not 32 pixels exactly. It depends on, for example, if you have AVX2, it might be doing 32 pixels. If you have AVX512, it might be doing 64 pixels. If you have only SEC4, it might be doing 16 pixels at a time, right? Like, it chooses the chunk size based on what's available on the hardware level, and that's something you can do quite trivially with RISC-V. You can just detect the vector length at runtime and choose the correct chunk size to iterate. So, in a way, this design would also very easily scale to whatever RISC-V implementation you throw at it. It would also be very easy on RISC-V, especially because you have sometimes conversions between different pixel sizes. Like you have, if you convert from 8-bit to 32 bits, you end up having to use like half a register for the 8-bit and then 2 registers for the 32-bit code. And with RISC-V LNOL, you can do that very, very easily. So I would personally even be interested in writing a RISC-V backend because that sounds like something that would be a good fit for the new design.